So the first question is that if a family is chosen at random and is found to have a boy, what is the probability that the other child in the family is also a boy? Okay. So that is one part of this question. Second part is if a child is chosen at random from these families and is found to be a boy, what is the probability that the other child in that family actually the question is the same, however the basic condition has changed. In the first part I am asking if a family is chosen at random and is found to have a boy, what is the probability that the other one is also a boy? In the second case I am saying if a child is chosen at random from these families and is found to be a boy, what is the probability that the other child in the family is also a boy? So let me explain the solution to this. So it is based on the your classical definition that we have to solve this problem, because we are assuming the occurrence of boys and girls equally likely. So in the first case, you are choosing a family. So a family can have two boys, first boy, second girl, or first girl, second boy, or both are girls. Okay. And the event A, let us consider that family has a boy, and let us consider B to be the event that the second child is also a boy. So let us look at this. We are asked to find out what is the conditional probability of B given A. That is probability of A intersection B divided by probability of B. Probability of A. Now what is probability of A intersection B? So it says family has a boy and the second child is also a boy. So this is corresponding to this element BB. So that is the probability is 1 by 4, because we have assumed equally likely for all the possibilities. And in the what is the probability of A? The family has a boy. So there are three cases in which family has a boy. So the probability will become 3 by 4. So the answer is 1 by 3.
So what's the difference between the B comma G and G comma B?
Yeah, so we are saying the families with two children. So the first child and the second child. So then B, G and GB. So first and second. Okay.
You mean
Is that
boy is
okay?
younger than girl and
So
the
it's
second
like
case girl is younger than.
tossing of two coins. Yes, yes.
Sir, but aren't B comma G and
Hello.
G comma D, sir, aren't B comma G and G comma B the same thing, sir? So why are
Yeah,
we
that's what
considering
I'm
them
saying.
separate things?
Yeah, we are considering them
Yes,
separate
sir. The
things
question
because
states
these are
that there are only two
identifiable
children.
people. Yeah, yeah.
So won't
So
the
this is
sample space have only
identifiable. So
three
therefore
outcomes?
ordering. Yeah. So here we are because this is human being, so they are identifiable. They are not identical. So BG and GB cannot be same. Okay. The order is taken into account here. The order has to be taken into account.
So using is identifiable,
Okay.
but boy and girl.
So is this
but we
clear?
are using these terms, boy and girl.
Yeah, so we are putting first, second, second, first. So like that. I mean, so that is why the difference is there.
Okay, okay. So.
I mean, you cannot make them indistinguishable. It is like if you consider tossing of two coins. So you look at head and tail on both. So TH and HT both are the members. We don't consider them as single. Then you will be losing. You will be making the same mistake what Cardano had made. Okay. See, once we are
Excuse me,
identifying
sir.
the sample space correctly, then there. Yeah.
Sir, if that was the case, then the question should have been like, if a family has chosen, family is chosen at random, and the first is a boy. It is, but it is given that it only has a boy, so it can be a first one or the second one, no?
That is what. So that is correct. That is why if you look at the probability of A, it is 3/4. It is not 2/4. Okay. If I say first is a boy, then it will be 2/4. But I am not saying first is a boy. I am saying family has a boy. So that is why it is 3/4.
Excuse me, sir.
Yes.
Sir, the event that event
Yes.
A, that family has a boy. Does this mean that there is exactly one boy in the family?
No. 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 Then I would not say that other one. I mean, if it has one boy, then the problem is identified. Na? I mean, then the problem is shortened. If you say one boy, then it will become only BG and GB. So the probability will become half. Okay. So let me move to the second part of this. In the second part, we are choosing a child. So now the description of the sample space will be different. See, this problem I am solving only to bring out this kind of thing. So here I am saying a child is chosen. So child can be a boy and or a girl. So if it is a boy, it may have another boy in the family, or it may have a sister, or if it is a girl, then the girl may have a brother, or the girl may have a sister. Okay. So actually there are two options, B and G, but because of the second possibility, the sample space will have 4 points here. Okay. The description is almost similar, but it is written in a different way now because my sampling unit has changed. Earlier I was saying a family is chosen. Now I am saying a child is chosen. So I am describing in a little bit different way. So now let us look at A event. The child is a boy. So what is the probability of A? That will become half. And B is the event that child has a brother. So what is the probability of A intersection B? That is 1/4. So probability of B given A, it becomes 1/4 divided by half, that is 1/2. So you can see obviously the difference between the two answers because the way the sampling is done, it is changing your answer. So this is what I wanted to bring out here. There are two types of tubes in an electronic gadget. It will cease to function if and only if one of each kind is defective. The probability that there is defective tube of second kind is 0.2. Sorry, the probability that there is a defective tube of the first kind is 0.1, and similarly the probability that there is a defective tube of second kind is 0.2. It is known that two tubes are defective. What is the probability that the gadget still works? So let us consider the event A, that two tubes are defective. And let us say B is the event that the gadget still works. So let us look at what is probability of A. So probability of A is say 0.1 square, that is both defectives are of the first kind or both are of the second kind, or one is of the first kind and another is of the second kind, and of course the ordering is taken care of. So this gives us 0.09. So what is probability of A intersection B? So A intersection B means two tubes are defective and the gadget is still working. That means both must be of the same kind, because if one of each type is there, then it will not function. Okay, so both are of the first kind, that is 0.1 square, and both are of the second kind, it is 0.2 square, that is of course 0.05. So what is the probability of B given A? It will become 5/9.
Sir, why ordering is taken care of here?
Yes, sir. Why have we multiplied it by 2?
Yeah, ordering will be important here. See, because these are identifiable things, no? See, if there is no distinction, then ordering will not matter. But here distinction will be there. Now, like if I say A and B, two type of things are there. So A or B. Okay, so ordering will matter here.
So, but we just so the point two into point one is one of first kind and second of the second kind. So if and this is the probability of them being defective. So I'm not understanding what's
Yes,
the sense
yes.
of ordering here.
Yeah, okay, let me just read the problem. There are two kinds of tubes in an electronic gadget. So it will cease to function if one of each kind is defective. Okay, so there are, I mean, like A type of things and B type of things. Okay, now we are saying one of A and one of B. See, they are placed in a gadget. Okay, now you
Yeah.
are saying that first one is defective or the second one is defective. Okay, so now first one is of which type? First one can be of the A type, second one can be of A type. First one can be of A type, second one can be of B type. First one can be of B type, second one can be A type. First one can be B type and second one can be B type. So here ordering will play a role. If ordering does not play a role, then the number of possibilities will reduce. Okay. So see, these are identifiable things. You have to understand the difference between identifiable and non-identifiable. If non-identifiable is there, then the probabilities will change. Since I am talking about certain things here, so they are identifiable. If that is not so, then of course the answer will change. So all the bolts in a machine come from either factory A or factory B. So with probability half, all are taken from factory A, and with probability half, all are taken from factory B. And the percentage of defective bolts is 5% from A and 1% from B. So two bolts are inspected. If the first is found to be good, what is the probability that the second is also good? And if the first is found to be defective, what is the probability that the second is also defective. So let us look at the solution here. Let us define event say G1 that the first bolt is good, and G2 let us define second bolt is also good. So we have to find out the probability of G2 given G1. Okay, so first of all, what is the probability of G1? So probability of G1, that means first is good given that it came from factory A into probability of A. We are applying the theorem of total probability here. Okay. So now this answer is known, probability of A and probability of B is half, because we are saying it is equally likely to come either from A or from B. And the probability of being good from A is 0.95, and the probability of being good from B is 0.99. So of course this is 0.97. So this is the probability that the first bolt is good. Okay. Now in a similar way we give the argument for the second one, that is G1 intersection G2. So again it is both are good given that they are from A, and probability that both are good given that they are from B. Here, because all of them are coming either from A or are from B, so therefore only this possibility can be there. We cannot have one coming from A and another coming from B. That possibility is not there. So this is then equal to 0.95 square into half plus 0.99 square into half. So this of course you can easily evaluate. It is 0.9704. Sorry, not this is sorry, there is a mistake here. Okay, so then we calculate the ratio probability of G2 given G1. So it is probability of G1 intersection G2 divided by probability of G1. So this we have calculated. So we just substitute the values, 0.9704. Yeah, you had some question?
Yes, sir. Sir, why are we not considering that the bolts can be from different factories?
No, that is the condition given here. The condition is given like this, that all the bolts come either from factory A or from factory B. Okay. So either we purchase everything from A or from B, but of course the probability is half. So that possibility which you are saying, that is not in the assumption. Okay.
Yes, sir.
Okay. Actually, what is the purpose of solving this problem? So what I am saying is that what is the probability that the second is good given that the first one is also good? It is 0.97. What is the probability that the first one is good? That is 0.97. So the probability has increased. What does it mean? It means that if the first one is good, then the chances that it came from a factory where the defective is less. So therefore the probability of second also being good is also so that should increase. Okay. Let us look at the second part so you will get more clarity on this. So in a similar way, if I say D1 is that the first bolt is defective, and D2 again second is defective. Okay. So what is the probability of D1? So it is probability of D1 given A into probability of A plus probability of D1 given B into probability of B. That is 0.05 into half plus 0.01 into half. So that is equal to 0.03. And if you look at probability of D1 intersection D2, then that is equal to, by the same argument, it will become 0.05 square into half plus 0.01 square into half. So you look at the ratio here, probability of D2 given D1, that is 13 by 300, that is greater than 0.03. So again here you can see that the conditional probability that the second is defective, given that the first one is also defective, increases. That means if the first is defective, then the more chances are there that the product has been taken from that factory which is having higher number of defectives. So it is called a property that probability of repetition increases. Okay. Examples of such things are abundant in real life situations. So if somebody is, if a certain organization or some other person, if rank is higher in a particular evaluation, then the chances that the rank will be higher in another evaluation is higher. The probability that it will be more is higher. Similarly, if someone is performing badly, then the chances that in the next one also the performance will be poor is high. So this we observe in our grading, we observe in our evaluation. It is observed by the evaluation of the countries in terms of growth, and there are many development indices. So for example, GDP, then you have health indices and so on. In all of that, it is observed that the probability of repetition increases. Okay, so it is justified in some sense. This is because, of course, we have made a theoretical model and we have solved a problem. This is happening like that. One more practical example of this you might have noticed. Of course, I think most of you have not had driven a automobile or something like that, or car. Maybe one or two of you might have done it because you have just crossed the age of 18. But maybe if you are familiar that in your family, if there is a automobile like a scooter or a motorcycle or a car, then if in the year 2019 there is a particular insurance taken, in the next year the insurance will increase if there is an accident claim. If there is no accident claim, then the insurance premium reduces. So in actuarial also these things are used, and I think some of you may specialized in actuarial, that is the insurance business also, and you will find this. So there is a problem related to this in your assignment and you will solve it. So I will not spend any more time on this here. So there is another problem where we will have certain application of the links and so on. So let me look at this problem. So you look at some sort of network here. These numbers which I am writing, they are the probabilities, okay? So you can consider it as, say, for example, an electric network, okay? It can be electric, electronic, or any other kind of mechanical network also. Basically, it means that the command flows from A to B. So in electrical, it will become current. In electronic, it may be data transfer or signal transfer. In mechanical, it could be just some shock transfer or pressure transfer or any kind of thing. So an electric network. Can you see the figure very clearly, whatever probabilities I have written?
Yes, sir.
Yes.
So we make the assumption that all the links are independent and these are represented as the probability of failures for the links. So from A to B, you have several channels. There is one channel here and here two links are there and each of them has a failure probability 1 by 5. Then there is a second channel which has a failure probability 1 by 3 and then there is a third route. Again here there are two links. Each of them has a probability of failure as 1 by 3. Okay. So we are asking the question, what is the probability? So, okay, for example, what is the probability that the current flows from A to B? Okay. So let us look at this. So we can consider the three paths as E1, E2, E3. Okay. So what is the probability of union EI? I is equal to 1 to 3. So because if at least one of the path is working, then the current will flow. In order to evaluate this, we look at 1 minus probability of union EI complement. So this is 1 minus probability of intersection EI complement. I is equal to 1 to 3. Since all the paths are considered to be independent, probability of intersection can be written as product of the probabilities. Now let us look at each of these probabilities. what is probability of say E1 complement? What is the probability of E2 complement? So E2 complement is simplest because E2 complement means that the second link is failed. That is probability is 1 by 3. So this will become simply 1 by 3. For the first one, the probability of failure is 1 by 5. So failure will happen if either of them fails or both of them they fail. So we can consider 1 minus that both of them are working. So it will become 1 minus 4 by 5 square. Similarly, if we consider E3 complement, so here again there are two links. In the third one, there are two links. So if both of them are working, then the system will work. So the probability of that will become 3 by 4 square. So if it is not working, it will become 1 minus 3 by 4 square. So you substitute all these probabilities in this expression and evaluate, then this will become, well, 379 by 400. The probability that the system is functioning is quite high. Okay, what is the meaning of high here? The meaning is that since there are three channels, three different paths are there, so the probability that all of them they fail will become much smaller. Okay, later on when I discuss the parallel and parallel links and also the link, I mean collinear links. So we will discuss this in detail in the reliability that has certain expressions there. I will discuss in detail later on. Right now, I just wanted to solve a direct problem. So is it okay? Is this clear?
Yes, sir.
Yes, sir.
Okay. So now I move to the next topic. So I think I have solved many problems, and that assignments and other things will be there. So you can look at that. I next move to the topic random variables. Okay. The font that I am using for pen, is it okay? Or is it bold?
Yes, sir, it's okay.
It is okay. Now you look at the problems that we have handled. We have looked at drawing of cards, we have looked at coin tossing, we have considered dice, we have considered gazette working, we have considered children, family, the number of children and so on. There are so many type of things are there. What happens that many times you are interested only in certain numbers. Whenever a random experiment is conducted, there are various facets to the experiment, but we are not interested in everything. We are interested in certain outcomes. So for example, yesterday cricket match ended in a draw. Okay, so there are many things, but how everyone was talking about certain records, that a player played 161 balls and he scored 23 runs. Then they said that after 40 years, it is the longest that the Indian team has batted in the fourth inning. So longest means they actually looked at how many number of overs they have faced. Actually, I'm in a class now. I'll call you later. Okay, so so finally it is reducing to certain numbers. So what happens that if we associate with each outcome a certain number, if with each outcome of the sample space we associate a real number, it is called a random variable. Okay, so the motivation for defining a random variable is clear, that we want to define, we want to handle the numbers, because ultimately physical description has limitations. We cannot continue to have physical description of the sample space and then we look at what is the probability of certain things. If we reduce it to numerics, things become easy to handle mathematically. So a random variable is a real valued function defined on the sample space. So we use this kind of notation. So let omega b p be a probability space. You are familiar with this terminology. Omega is the sample space which is outcome of a random experiment. B is the corresponding event space which is nothing but a sigma field, and P is the probability function defined on that. Okay. So we have a probability space. So a random variable X. Okay. So we are saying it's a function. So function, generally we use the notation f, g and so on in mathematics, but here I am using capital English letters like x, y, z and so on. So this is a function from omega into r. Technically we put a condition of measurability, but I will not talk about that at this moment, because what happens that every subset here, because B is the event space, so for every event space, every set in the event space, each element is corresponding to something. So basically we have a condition that on the right hand side also you will have a subset. So this omega goes to r, so B goes to something called say C, okay, and then this P goes to Q, because we were defining probability of A here. Now corresponding to A there will be a set here, okay. Suppose A goes to a set E, okay, belonging to C, because A is the set of certain outcomes, because this is a subset of the sample space. Now corresponding to each element of the sample space there is a real number associated, so there will be a corresponding set E in this. So therefore now this probability A is same as some probability which is related to E, but I will call it Q now because P we have already used, so I am just giving another name here. So this omega BP is shifted to your RCQ if we use a random variable X.
Sir,
Yes.
sir, what does this C and Q signify over here?
Yeah. So I'll just tell you. Yeah. So let us look at with a very simple example. Okay. Let us look at with a very simple example. Let us consider tossing of a single coin. Okay. Suppose a fair coin is tossed once. Okay, only once. So I think I made the problem very, very simple. So your omega is HT, and what is your B? B you may consider say phi, H, T and omega. Okay. And you can associate the probabilities for each of them. What is the probability of phi? That is 0. What is the probability of H? That is half. What is the probability of T? That is half. What is the probability of omega? That is 1. So now I consider the random variable X as the number of heads. So what are the possible values? Omega has two elements. X of H is 1 and X of T is 0. Okay. Only two possibilities are there. So only two values this random variable X is taking. So then what is C that will happen? because corresponding to everything, what is the corresponding element there? Like H is going to 1, T is going to 0, and phi remains of course phi, and omega becomes R, the full space. And we have assigned the probabilities. What is Q of 1? That is half. Q of 0, that is half. And of course, Q of phi remains 0 and Q of R will remain 1. Okay, that I don't have to write.
So can you repeat from that x number of heads?
So let me explain. Yeah. Hello? Yeah. Okay. ना आप किसी को assign कर दिया करिए, because see, whenever something is coming urgently, then I have to just send it, because it is mostly coming from director's office. So so आप मतलब थोड़ा देख लीजिए अपना लेवल पे किस तरीके से हैंडल करना है, ठीक है, क्योंकि वो सब लास्ट मिनट पे ही आता है वो जो है. नो इट इज ऑल राइट. ठीक है, आप देख लीजिए. ओके फाइन. ठीक. या ओके. Yeah, so let me repeat the we are considering a random experiment of tossing of a fair coin once. So you have two outcomes, H and T, and I am considering the sigma field of subsets of omega by considering power set basically. So phi, H, T and omega, and probability of phi is 0, probability of H is half, probability of T is half, and probability of omega is 1. I am defining the random variable x to be number of heads. So H goes to 1 and T goes to 0. So what is happening to B, the sets of B, where they go? So phi of course goes to phi, H goes to 1 and T goes to 0 and omega goes to R. Okay. See, we may not write here R, we may write only 0, 1 also. Okay, we may write just 0, 1, that is also enough. I just wrote R because we are considering this one, but we may consider only 0, 1 also. Okay. And then we have this probabilities associated with each of these sets. So what happens to the corresponding probabilities here? So for example, for 1 the probability was half, for H the probability was half. So probability that, so actually we will write it like this. Later on the statement will become like this: probability of X is 1 is half, and this will be probability that X is equal to 0 is half. That's all. This will be written finally, but I am writing theoretical expressions actually just to explain the concept that how the things have got modified here. I can remove this here. Okay. So is it clear from the, we have a probability space omega BP, and using a random variable we are transforming that space to another space which I am calling RCQ. This need not be full R, it could be a subset of R, but I am just writing there. Okay. Is it okay? You have some questions?
Yes, sir. It's
Yes, sir.
Sir, could you please again explain why is x of h is equals to 1 and x of t equal to 0?
So we are defining X to be the number of heads. So if H comes, the number of head is 1, and if the tail comes, then the number of heads is 0. So H is 1 and XT is 0.
Okay.
Is that all right?
Yes, sir.
Yes, sir.
Yes,
Okay,
sir.
so in next class, I will be talking about the probability distributions. So actually, I have already given you a brief understanding of the probability distribution through this assignment, that P goes to Q. Okay, so now you already have an elementary understanding of the concept of probability distribution of a random variable, but I will talk in a more formal sense in the next class. Okay. As I have already explained to you that I am going to post the assignment today. So you please solve the problems, and there will be certain, so we are not asking you to submit the assignments because that will be too complicated. Because now we are seeing that in each section there are around 230 or 240 students. In fact, I think in section 1 it is 247 now. So it's because the number has crossed to 900, almost 940 students are there. So we will not be able to do evaluations like that, and we will be conducting some tests only. And we will starting from the next week, the tests will be conducted. We will intimate you about how the tests are conducted. And please follow your sections carefully, because I have very clearly given the guideline that which student is in which section. Okay. And if you violate that, then there you may get into some trouble when the grading etc. is done. So I hope all the students are very clear about the sections. And if you are not following the section, please do that. All the students which are prior to 2019 batch, they must attend section 4. And all the students of BT, CS and CH, they should attend the section 3. And all the students of mechanical and this one, and the students of mechanical and then civil engineering and industrial engineering, they must attend section 2. And all the students of 2019 batch other than this, they must attend section 1. And all the students of mathematics and QE, QM and mining, they must attend section 4. And all the students which are prior to 2019 batch, they must attend. So I am clarifying here again, that is students up to 2019 batch I am saying separately, and all the students which are other than 2019 batch, they must attend the remaining, the section 4. Okay. So let us close this class now. Okay.